kinematics in one dimension. This is probably the first thing that you guys did in class, but we're going to review it just to make sure that everybody is okay with it. The definition of kinematics is just stuff moving. And then one dimension is a line. So kinematics in one dimension essentially says stuff moving in a line. I guess a little bit more explicitly said is this is the part of mechanics that deals with mathematical descriptions of motion. Way more boring than stuff moving. But we don't care about the forces on the object. That's something that we will be getting to later, something that will be very, very important later. But for this part of the class, we don't care at all about forces. All that is already taken care of us. Kinematic equations, they're going to be giving us a bunch of different variables, such as position, velocity, acceleration, and time. You know, if you're an engineer, you're probably going to be having to deal with the next step after acceleration, which is jerk. We're not going to cover that at all. And let me see if, do I go over this? Yeah, okay. So these, we're not going to worry about jerk right now. These four variables are going to be very, very important to us. And I'll teach you guys how to use them, or I guess review how to use them. So we're only caring about direction in a single line. Forward is shown with a positive sign. Backwards is shown with a negative sign. If something moves negative 10 meters, that means it's moving 10 meters backwards, or to the left or to the right. Any of our variables can be negative. So again, position, a negative variable is just 10 meters behind you. A negative velocity means that you're moving behind, like you're backing up. Positive means you're going forward. An acceleration means that you are accelerating backwards, and then a positive is you're accelerating forward. Please do note that you can have a positive velocity and a negative acceleration. Or you could have a negative velocity and a positive acceleration. I mean, you can also have, you know, positive and positive, or negative and negative. If they're the same signs, that means it is, quote unquote, speeding up. So if you are moving forward and you're also accelerating forward, that means you're starting to go even faster. If the signs are negative, this is slowing down. So if you're going forward, but you're starting to slow, you're going to slow, and you're eventually going to stop, and then you're going to start walking backwards again. That is what happens when you have velocity and acceleration with different signs. Even our time variable can be negative. It's not usually used, but if you say that something occurred at negative 10 seconds, that means it happened 10 seconds before we started our experiment. Most experiments are going to do what's called a zero, where we choose our initial condition at time equals 0. That will not always be the case, but pay attention to that. Yeah, to make our lives easier, we'll always assume that time is greater than or equal to 0. There are 4 very important equations that you're going to need to know for this. I'll give them in their more complicated forms, and then there are also simplified forms. This one is the final position is equal to the initial position plus the average velocity times t minus the initial time, which a lot of times we will set up our t0 to be equal to 0 seconds. So oftentimes this is going to just simplify to x final is equal to x naught plus the average velocity times how long it's been moving. There are a bunch of constants in this. X naught is the initial position. That's where it is at t equals 0. The average velocity is the average velocity over the whole time. It's not the instantaneous velocity. It's, the average value of that. We can write that average value as this division right here between what the x is now and what the x was, and then the t is now and what the t was. Okay, that was the first equation. This is the second equation. It looks so similar to this that it's like, okay, it's just the same thing. Again, we can also write our v final is equal to v initial plus the average acceleration times time. V naught is the initial velocity, which is a constant. The average a is the average velocity. Oh, that should be acceleration. It can be written as that way. Type yes in the chat if you have seen these things before. Sweet. Very, very good. Feel free to ask questions about them if you don't quite understand them, but that is good that you've seen them. Another equation that we use is very similar to the one that we had before, but instead of time in the parentheses, we have position in the parentheses. And certain of these things are getting squared. If our initial x is 0, so if x is 0 is equal to 0, then we can write this as v final squared is v initial squared plus 2 average a times x. You use this equation if you want to solve independently of the time. So maybe you're not given the time, maybe you're trying to find the time later. This is when you would use this equation. And finally, the most important equation, the one where all these other ones come from, is this equation right here. If we set our t0 equal to 0, then we have x final is equal to x initial plus v naught times t plus 1/2 average a times t squared. This right here is a quadratic equation. So if we plug this into a calculator with t as our independent variable, we should be getting something that looks like a parabola. Maybe that parabola is shifted over here. Maybe it's opening downwards if the acceleration is negative. But whatever we get, it should be a parabola, assuming, of course, that this is non-zero. If the average acceleration is non-zero, or if it is 0, then instead of giving this parabola, we'll be getting some sort of line that's either up or down or whatever. This equation right here is actually all of the other equations put together. I'm not really going to prove that to you, but you can sort of see some of these equations within the others. When we graph these motions, we can see that position, velocity, and acceleration are all related to one another. They can be plotted versus time to show the graphs of motion. And so this is an example of 3 different graphs of motion, one showing position right here, one showing velocity, which is this one right here, and acceleration. If you guys have had calculus, do you guys know how to do derivatives? Is that a fair question to ask? There's a common bug with this simulation. If you reset it and then you set up the simulation again, you run it, and then you play it back, the values don't change here. That's unfortunate. The only way that I have found to get that to not be the case is just to refresh the entire page. And when you refresh the entire page and you set it up again and run it, it should work. So if you run into that issue, that's how you solve it. Okay. Are there any questions about this simulation? Does it seem pretty straightforward to you all? Seems legit, yeah, you know. This topic is not super hard. Just be very, very sure that when you're doing your calculations, you actually show your work. And, you know, I did also mention that I would be giving you guys answers. There's one question on this lab report that is a little bit trickier than others. Actually, there's two that are tricky on this one. Setting initial position, initial velocity, and initial acceleration. What we can do instead is click on this use a function, and you'll leave the velocity and the acceleration stops blank, but you can type in a function for your position graph. Now, look at this right here. This one has a sine of t graph right here. Interesting, huh? Okay, what does that look like? Okay, so this is going on. Oh, okay, this person's just going back and forth. He's oscillating between 2 points. Okay, cool.